Hello everyone, let us start the new question paper, that is June 2020, the organic part from the CSIR-NET. Okay. So, we are going to do the first 5 questions of the organic. So, the question says the correct IUPAC name for the following molecule is. Now, let us understand in totality about the IUPAC naming of cycloalkenes. So, when you have monosubstituted cycloalkene, what you have to do is you have to count it in such a way that substituent comes closest to the alkene part. Now, you cannot count it something like this, because if you count it something like this, you are not taking care of both the atoms. So, both the atoms have to be taken care and the substituent should be closest. Now, I cannot count it here because it is coming more distance, right. This is the right one because here you are counting both the carbons of the alkene and this is nearest from the alkene. This substituent methyl is nearest to the alkene. Okay. Now, if on alkene 2 substituents are there, then how do we name them? So, we give preference according to the alphabetical order. Now, this is ethyl, this is propyl, okay, methane, ethane, propyl. So, ethyl E comes before P, so we have to count from here. So, it will be 1 ethyl 2 propyl cyclohexene, right. Whereas, here if you see it is butyl and ethyl. So, B comes first, B gets first preference. So, it will be 1 butyl 2 ethyl cyclohexene, right. Now, let us look at our question. Now, our question, it looks like this should get preference 1 2 3, yeah, this should get preference because it is ethyl and this is propyl, but it is not just about the di substitution. We have to look at the substitution on the ring, that is very important. That should get lower numbering. So, if I give this one and these two according to the substituent, because ethyl gets more preference over propyl, then this gets the numbering gets very low. So, it will become 3, 4, 5, 6. So, it is a very long chain. So, that is not right. So, here we have to count from that part of the alkene, so that you get lowest numbering for the substituent on the ring. So, this gets first, this gets second, this gets third and this gets fourth, right. And how many carbons are there? 5, 6, 7, right. 7 are there. So, it is cycloheptene. At position 1 I am having propyl, at position 2 I am having ethyl, and position 4 I am having dimethyl. So, again while writing the substituent we have to write alphabetical order. So, first will come ethyl. So, it will be 2 ethyl, then comes methyl 4 dimethyl, then comes propyl 1 propyl cycloheptene. Okay. So, 2 ethyl 4 dimethyl 1 propyl cyclohept 1 ene. Yeah, otherwise you not written 1 ene also, it's all right. Okay. So, the answer is option number B. Next question. So, now it says muscone is terpenoid, polyketide, steroid, flavonoid. Now, this is tough question unless you have seen. So, I have tried to explain whole thing. Steroid, you can see it will be always 4 rings fused, something like this structure will always be there. So, if that is not there, it is not steroid. So, this is not there. Polyketide, from the name it suggests that it should have many ketonic groups. So, they have alternate ketonic group. So, our molecule does not have even that. Then flavonoid is basically 2 phenyl rings are there and 1 heteroatom is there, pretty much like this. Most of the flavonoids will have some structure like this. Whereas terpenoid, what happens? Terpenoid will be also always polymer of 5. It will multiple of 5 because its starting unit is isoprene. Okay, is isoprene which polymerizes to form here. Okay. So, here you can see it has basically 15 carbons are there. So, it is sesquiterpenoid and 1 methyl substituent is separate. Okay. So, this is a terpenoid. Answer is option number A. Next question. The following carboxylic acid undergoes decarboxylation upon heating. The case of decarboxylation is in the order. So, you are decarboxylating is basically you are removing COOET, hydrogen will go and attach itself. So, it is asking which will undergo fastest, which will go lowest and which will be intermediate, right. So, Hammock did a extensive study about decarboxylation on the heteroaromatic carboxylic acid system. So, let us look at the molecule T1 which actually he studied. So what he found out that they always undergo decarboxylation. Initially they form by the process, initially they form deuterium followed by decarboxylation with formation of carbanion. Okay, so let us look at this. So first what happens, you know, this nitrogen is there, nitrogen is basic in nature and this proton is acidic because it is carboxylic acid. So first step is deuterium formation, so it is plus minus. Then what happens, these two forms coordinate, see, then they will form hydrogen bonding, kind of stabilization occurs. And then what happens is this goes here, this comes here, and you get a negative charge on this system. This is very important. This makes reaction fast, otherwise you would not have lost, because negative charge on a carbon next to nitrogen which has positive charge. First of all, nitrogen is more electronegative than carbon. Apart from that, it has positive charge, so highly electronegative, right? It needs electron and you are providing electron just next door, so it's quite stable intermediate and therefore this is faster. So very clearly molecule 2 will undergo fastest. And then let's look at molecule 1 and molecule 3. Molecule 1, you can see there is no assistance whatsoever. Let us look at molecule 3 and find out is it becoming stable or less stable. Please understand, first step always will be deuterium formation. So how does it occur here? So here what happens, on the ipso carbon this comes and picks up proton, so that you get deuterium here. Okay, so it picks up proton and you get here. Now if decarboxylation occurs, you can see here, this comes here, this comes here, you get a negative charge on this. This should have been drawn little more this way. Okay, I'm sorry, this arrow was not very proper, but yeah, you get negative charge here. Now this is highly unstable. Why? Because you are getting negative charge next to a positive charge. Positive charge, oh I'm so sorry. Okay, you get this, and then this negative charge is stabilized over here, you get a pi bond. Of course, positive negative next to each other, you get a pi bond. Now what happens is, I'm so sorry. Okay, I got a little bit, I missed it. What you get is a positive charge here next to the nitrogen. Now nitrogen is electronegative in nature, you know that. So now when it is having when it is electronegative, it wants electron, but what you are giving? You are giving it positive charge, right? This is the final product. I missed it, I came up to this step. So this is a positive charge, so highly unstable transition state. So this decarboxylation will be toughest, because previous case we saw we got negative charge next to nitrogen with positive charge, whereas here we are getting positive charge next to nitrogen, electronegative nitrogen, so it is unstable. So this will be least reactive, this will be slowest, whereas B will be fastest. So first will be the most active will be second one, so this is the answer, yeah, and third will be slowest and first one is in middle, right? Moving on to the next question. The major product formed in the following reaction. This was quite tough question. Okay, first let us understand, this is HClO4, very powerful acid. Okay, see here something like this. So oxygen, generally ether, ketone, they are very low, basicity is very low, they don't easily go and accept proton, but this is so powerful acid that even this will get protonated and you get this species. Now what happens, this is 3-membered ring, you know, highly unstable because very strained, it has angle 60 degrees bond angle. Okay, then what happens, then this will open up. How it opens up? This comes here, this comes here, this opens up and you get positive charge here. So now there are two canonical structures possible, this positive charge, this will come here, this will come here. Now what happens, positive charge is of course not stable, it has to stabilize. So one thing is there, kinetically it is possible, like it is very favorable, if this lone pair comes here and this moves out here, you know, this acts as a very good electrophile. Positive charge is a vacant p orbital is the best electrophile, but what happens here is it is kinetically very favorable because just neighboring, you understand, there is a vacant p orbital and there is bonding orbital which has electrons, and it is being pushed because this lone pair gives electron in the anti-bonding, and therefore this bonding orbital becomes weak. This will move out here and you get this, and then what happens, this will pick up a proton and you get this. But this is not stable at all. Why? Because it became non-conjugated system. If whole system is conjugated, electrons like to be delocalized, but here this is creating a big problem. So rather than going through a kinetically favorable transition state, it goes to kinetically less favorable transition state. Okay, so what it does is, again lone pair pumps electron here, hydride shift to position from position 1 to position 4. It goes through 5 members. So 5 member ring is kinetically quite favorable, not as favorable as 3 member ring, but still quite favorable. You can see here it is 1, this is 2, this is 3, this is 4, this is 5. 5 member ring is kinetically quite favorable, thermodynamically also very favorable. Now what happens, this comes and hydride shift occurs here, you get positive charge here. Now you are getting a conjugated system, and therefore the answer is option number B. Okay, next question. The following transformation involves a series of, so it says these are the things, tell us what is the series of reactions. So is it electrocyclic ring opening and closing, cycloaddition and cycloreversion, sigmatropic arrangement, or kilotropic addition and elimination reaction? So first step is actually a 1,3 dipolar cycloaddition reaction. Whoever has cleared them, please open this chapter and find in the index 1,3 dipolar cycloaddition. Very important, many questions come many a times. Okay, otherwise just Google it, you should know this. It's simple, generally there will be Zwitter ion plus and minus next to each other. Then this is the 1,3 dipole and this is dipolophile. So dipole, positive and negative. So though it is positive, it pulls away all the electron density towards itself. Pi electrons are like cloud, completely shifts off here. So actually you have the positive polarity here on the C rather than B. B is pretty much neutral, though we write positive charge because of classical thing, but whole electrons is taken by B. So C is having positive and A is having negative, that's why it is dipole, and this gets attached alkene, so it is dipolophile. So a reaction occurs something like this. This negative charge attacks here, this comes here, this comes here. So here also is pretty much happening same thing. This electron comes here, you get a negative, so negative, positive, and you will have dipolophile here, correct? Because it is positive, it will pull away all the electron towards itself and you get positive charge here, positive polarity here rather. And so this alkene in the cyclooctatetraene, one of the double bond will act as, not tetraene, diene, sorry, okay, it will act as a dipolophile. So this goes and attacks here, we saw very clearly it was not attacking on a positive charge, it attacks on the positive polarity. This comes here, this goes and you get this. So this is first step of cycloaddition. Next what happens, it's reversion, this comes out and this carbon CO3 is lost, so cycloreversion, you get positive charge. Then again it undergoes cycloaddition, this negative charge, again it is same thing, 1,3 dipole. So this goes and attacks here, this comes and attacks here, this goes here, and you get this structure. So it is series of cycloaddition and cycloreversion reaction. So the answer is option B. Right, that's it for this video. Thank you.